So I want to talk about our most conspicuous trait. And it's something I'm doing right now. It's that we're bipedal. We locomote primarily upright and on two legs. Now it might seem normal for us, because we always think that everything we do is kind of normal. But if you really pay attention and kind of look around, nothing really else is doing it. Especially not any other apes. So why? Why did we evolve to move this way? So to understand why we walk around on two legs, you have to really consider the costs and benefits associated with being bipedal. Now, compared to all the other apes, we are very slow, horribly unathletic, can't climb trees, so it seems to be quite problematic. I mean, the fastest human being ever, Usain Bolt, he can't even outrun a house cat. And even then, he can't maintain that top speed for very long. And also, try running full speed at pace and making a quick maneuver. You're either going to fall or you're going to get injured. Either way, it's not going to go well for you. And even if you're a well-conditioned athlete and training, even then, side-to-side movements can result in injuries. You see, again, well-conditioned professional athletes are constantly plagued with knee injuries and ankle injuries because the skeleton just does not seem to be built for athletic ventures. So what are the benefits of being bipedal? Well, a lot of individuals will initially point out that, oh, being bipedal, well, it allows us to have our hands free and use tools, but that's part of this general misconception in evolutionary biology of what a trait actually evolved, what a trait actually evolved for versus what a trait is useful for. So think of it this way. If we were going to be bipedal to use tools, well, it's not just a matter of being bipedal. You still have to have selection on your hands to shorten your fingers, give you strong, robust thumbs, and you also have to have the intelligence to do this. So all those traits would have to evolve in concert for it to actually be the reason that we're bipedal. A corresponding example that might be useful is with flight, how flight evolved in the birds. Now you think of what adaptations are very useful for birds to fly. They have hollow bones, which makes them light. They have feathers, which allow them to, again, be light and capture the air when they're moving. However, those features did not evolve for the purpose of flight. Those features actually evolved independently on their own. So for example, dinosaurs evolved, a lineage of dinosaurs, evolved those hollow honeycomb-shaped bones to be lighter, faster, and more efficient. They later evolved extensions on their scales extended to form feathers, which again, useful for thermal regulation. So ultimately they initially evolved hollow bones to be efficient. They evolved feathers later on to regulate their body temperature for thermal regulation. Then after those features popped up, that changes the conditions now for selection to act. Then selection can act on additional features and cause the evolution of flight. So there's nothing inevitable about the evolution of flight in dinosaurs. Only once they evolved their hollow bones and the feathers, then again the conditions change to then allow selection for flight. So ultimately, having hollow bones had to be useful in its own right. Having feathers had to be useful in its own right. Then again, collectively, later on, those traits can be co-opted for this new trait or new feature of flight. Same thing with being bipedal. Bipedalism evolved at least 7 million years ago, but tools really didn't appear until about 2.5 million years ago. So when you look at the evolution of bipedalism, you have to really consider comparing a biped that can't make tools to a quadruped that can't make tools. And that's going to be the relevant comparison. So what are the advantages of being bipedal in its own right? One is you can carry resources. We see that chimpanzees do this when resources are rare. They will kind of pop up on two legs and be able to sort of carry resources around with them. That doesn't seem to me a reason to be bipedal all the time, considering they can do it just fine when they need to. Another advantage could be thermal regulation. By being on two legs, I'm exposed to less sunlight hitting me, striking down than if I was on all fours. Again, that seems to be quite a benefit of it, but is that the reason that it evolved? Particularly because we did evolve in the woodlands, so it doesn't seem like that would be a major selection force initially. Other advantages could be to be able to look out for predators. You can see over tall grass and see where things are coming, things might be coming up to surprise you. However, if you're going to be slow, what's the point of really seeing something if you can't really get away from it? But ultimately, those are advantages of being bipedal, but is that the reason that it actually evolved? Well, it turns out that the likely reason that bipedalism evolved is purely based on efficiency. It's just much more efficient to walk around on two legs than it is on four. For humans, we spend about a quarter of the energy walking on two legs in any given distance compared to, say, a chimpanzee that's walking around on all four legs. Now, this could be definitely advantageous, particularly during the time that bipedalism first started emerging. And that was a time where the climate on the planet really started deteriorating and getting much colder. So, apes really emerged in Africa about 20 million years ago. But about 10 million years ago, the climate started to change. It started getting colder, so these forests that we were living in started getting broken apart. So now, instead of hopping from tree to tree to tree and getting enough resources that way, or enough fruits and that way, now you have to travel greater distances between these trees to actually be able to forage effectively. So if you can walk around bipedally, compared to, say, a chimpanzee, you can cover 4 times the amount of area at the same cost as it would take a chimpanzee. So ultimately, that efficiency, despite the lack of speed, reduced ability to climb, and overall reduced athletic ability, we're able to save so much energy, which allows us to cover a greater amount of area to collect those resources. So those are the advantages, or that's the advantage of being bipedal, just purely saving in efficiency, or increasing efficiency in foraging. And you could think that selection, just like it's going to favor traits that might allow you to capture more food, to increase the amount of calories you're bringing in, adaptations that allow you to save calories and be more efficient should be favored just as much. So what are the adaptations? What are these traits that we needed to allow us to be bipedal? And when did these actually start popping up? Well, I'm going to start from basically the head and then work my way all the way down. And I'll try to talk about some of these adaptations, what they're useful for, and again, when did these actually start emerging? So first up, it's basically, you might as well start at the top. If you're going to be bipedal, you want to make sure that you're still looking forward when you're walking. And if you think of how a quadruped's walking around, even like a chimpanzee or even a dog, you notice that its neck comes off the back of its head, because that way when it's on all fours, it's not staring at the ground, it's staring straight ahead. So if you're going to be bipedal, you want your neck to come off the base of your skull. And we actually found that in the first of the bipedal hominids, Sahelanthropus. All they found was actually the skull of this ape, and they're able to infer that it was bipedal because, again, the position of the neck or where the neck comes off the base of the skull. So the foramen magnum, which is basically that hole, that connection, that in Sahelanthropus is closer to the bottom, similar to us, than to the back, which you tend to find in chimpanzees. So even though we only have the skull, we know that about 7 million years ago that this ape was capable of bipedalism. So next we should also think about our backs. When you're a quadruped, your back basically forms like an arch, and then you could think of the legs coming off it like pillars. So think of a horse. If you're sitting on the back of a horse, you're sitting basically on this archway. So it's this nice arch, you're sitting right on the top of it, these two pillars holding up. Again, very effective at managing that weight that's pulling down. But ultimately, if you want to stand this thing up, you have to add a couple more curves into the back. So the big one, the big lordotic curve at the base of your back down here, in your lower back. Now those lumbar vertebrae down there are wedge-shaped, kind of like little triangles, like this. They're wedge-shaped, so that allows this back to have that lordotic curve, and then you have the same curve, that kyphotic curve that you can see in the quadrupeds. So that lower back, those lumbar vertebrae, we have anywhere from 5 to 6, it really depends who you are, of these lumbar vertebrae that are in this shape. Chimpanzees have about 3. However, you do find chimpanzees that have 4 and 5. So there you can see there's actually a lot of variation there for selection act on, even within the current quadruped apes. So another, going down the line here, the next basic structure to really consider when it comes to bipedalism is actually the pelvis. So if you think of the pelvis right here, ours is much shorter, and its position is also changed. And it flares out to the side. So I'm going to break down those specifically. So the pelvis is much shorter, and that's quite important because in chimpanzees, you can see that the pelvis goes all the way up and touches the rib cage. So ultimately, they cannot swing their torso and their hips independently. They can't do this. Because their pelvis goes up into their ribs, everything has to move together. Their hips and their torso have to move in the same fashion. They do have quite an ability to swivel their hips to sort of accommodate for this quite a bit, but again, they can't do this sort of independent rotating motion. Also, our pelvis is sort of rocked back. Instead of being positioned forward, like here, instead of pushing it forward to kind of have the animal's body kind of keep lurching forward as a quadruped, ours is rocked back like so. And that way, our torso can kind of sit inside of that pelvis, like almost like a cup just holding it in. So that's also quite important. Another interesting or important aspect of the pelvis is that the iliums, you see this upper part of your pelvis, they flare out heavily to the sides. And that allows actually for some of these stabilizing muscles that allow you to stand on one leg. You can kind of go like this. It allows for those muscles to attach here. In chimpanzees, those same muscles will actually go back. So the muscles that we would use to, say, move our legs off to the side like so, for them, using that same muscle will cause their leg to sort of go back. So they don't really have the ability to stand on one leg. And if you're going to be bipedal, you have to be constantly balancing and stabilizing on that one leg. Another important feature along with that is that our femurs, when they come off of our pelvis, they actually angle more inward, and that keeps your center of gravity more towards the center. And ultimately, again, when you're walking and you're taking one step at a time, you're balancing on one leg, and you also want that leg to be striking relatively in the middle of where your weight distribution is. Now, we noticed some of these changes in some of the earlier bipeds. As I mentioned before, Sahelanthropus, about 7 million years ago. We know that the neck was coming off the base of the skull, but we didn't know anything about the rest of its body. The next hominin we have any evidence for is Aurorin. In Aurorin, we have basically just the hip, just the proximal end of the hip. And with that, you can actually infer a little bit about the angle it's coming off the pelvis, and some about also just compares general physiology of that part of the hip to, say, quadruped apes from, say, the Miocene, maybe 10, 20 million years ago, and compare that hip again to some of the apes we knew were capable of bipedalism later on. And we find in Aurorin, just by only having this little small region of the hip, we could find that the shape of that hip is somewhere in the middle, basically, between the quadrupeds and the biped apes. So we can kind of, again, infer a little bit about the hip action with them. But the later big finds in these walking apes, essentially, were with Ardipithecus and Australopithecus. So Ardipithecus, this genus evolved about 5 million years ago. And what we could see from them, we have many more bones in these organisms that we can actually look at. So what we can see here from their hips, that their hips actually is much lower. There's much shorter hip, or much shorter pelvis. So you can see that they were sort of allowed to basically move independently. Now the next adaptation I want to talk about further down the line is really our feet. So all this down here. Now that's going to look very different than a quadruped's ape's foot. Things that are maybe easy to point out. For one, we have shorter toes, really short toes, a big, robust big toe. And the reason for that is, again, you want to have sort of a firm foot to strike the ground on. And if your toes are really long, again, might be useful for climbing trees, but kind of messy when you're talking about running quite quickly. Just think of a horse that's just striking the ground with basically just its toe. So ultimately, you don't want to have long, sprawling toes. Also, with the toes, they could bend backwards like this. They're capable of that hyperextension. And the reason for that is, obviously, if you're going to roll onto the front of your foot, these guys need to actually be able to bend a little, and also a nice robust big toe to sort of toe off of. So that's one feature. Another feature is the overall stiffened outer foot, or the stiffened foot in general. And that's, again, it's important because you don't want the foot to hit the ground. And say if you're walking on your hands, not stiff, and you can see how it sort of falls apart if you put all your weight on your hands and try to walk on your hands. So you really want a stiff foot. And part of that stiffness in the foot is accomplished through the arch. Now the arch is layers of muscle and tendon that really allow sort of the spring shape. Again, not like a coiled spring, but a spring shape like this. Now what that does is, if this arch hits the ground and it flattens, now you're loading that spring, and that'll help you sort of push off. So when it deforms, you're loading that spring with some of the energy you're putting into the ground, and you get to return that and help you again push forward. That's an adaptation that's mostly useful for actually running as opposed to walking, but still important to point out. And then probably another one of the prominent features is the large heel pad here. If you're going to be walking, again, on only 2 legs, then you really want to have that heel pad to sort of absorb that impact when you're walking. So ultimately, you have the heel pad, the stiffened foot, shorter toes, and also the rounded joints that are able for hyperextension to allow you to sort of push off. So when did these features pop up? Well, we know from Ardipithecus about 5 million years ago. Again, she had, what I mentioned before, Ardi had a lower pelvis that didn't articulate with her rib cage, and she also had her limbs were flaring out to the sides. And we also noticed that Ardi had a stiffened outer foot. She had long toes still, so clearly capable of still climbing in trees, and also long arms. It basically looked like a chimpanzee with a slightly stiffened outer foot. So she was still an accomplished climber in trees, but capable of walking bipedally. So now I want to talk about some of these traits in the context of Australopithecus. These were bipedal hominids around 4 million years ago. The very famous find was Lucy. So Australopithecus, we know that we have plenty of their skeletons, so we can really infer that they were quite capable walkers. Now, Australopithecus had, again, much shorter pelvis. And interestingly enough, one of the downsides of actually being bipedal is pregnancy and childbirth. The smaller this is more functional for being bipedal. Not so great for pushing babies out. So we know with Australopithecus, because their hips were getting smaller and smaller and smaller, the baby actually had to be born with its head turned to the side in order to fit out. On humans, when you shrink that down even more, the baby actually has to kind of do some crazy gymnastics just to get out of there, kind of twist around and rotate in order to squeeze out. So anyway, with Australopithecus, again, we noticed this reduced, again, size pelvis. We also see that they do have a stiffened foot, much more so than Ardipithecus. So they have a somewhat of remnant of an arch there. Much shorter toes. And interestingly enough, we have footprints of Australopithecus preserved in volcanic ash from 3.6 million years ago. They're called the Laetoli footprints, and these are from Tanzania, which is a country in East Africa. So they had a few of these individuals. You could see that they were walking across this sort of this plain, and interestingly enough, because their footprints are preserved sort of in the ground, you can see that they had almost an indistinguishable gait than we did. So they were capable of almost exact same strides that we were. So they were certainly very good long distance walkers, or very capable long distance walkers. Now there's other adaptations that kind of pop up after the fact, or after that lineage into our lineage Homo, that really made us better runners, not just walkers but better runners. Like a full arch, well buttressed knees and ankles to really handle that load, and then you could think shorter arms, a more barrel chest, and also other features such as reduction of the fur so that we can actually sweat while we're running, the shape of our nose, many other adaptations that I really don't want to get into right now. But anyway, next I want to talk about how running shoes have actually interacted with some of these various adaptations. So I want to talk about shoes in the context of evolution as us being runners, and hunter-gatherers. So there's an interesting debate on whether you should run, barefoot or with shoes. And both sides of this debate, they have legitimate points. For example, if we say, okay, you should run barefoot. Well, humans have been running for millions of years. So clearly we have to have adaptations to be able to handle running around without shoes. So one of these adaptations are actually calluses that you will develop on the bottom of your feet. So you think initially, like, how could we run barefoot? If you run outside right now, it would be very uncomfortable. But if you did this for a prolonged period, you'll develop calluses on the bottom of your feet, just like if you were lifting weights, barehanded or dealing with abrasive materials in your hands, you'll develop calluses on your hands. Same idea. If you're going to be scampering up trees, you need to develop some kind of protective layer on your hands. And if you're going to be running around, obviously using your feet as what's impacting the surface, you should have protective layers there. So these calluses that you will develop over time are substantial. They're loaded with keratin. This is very strong material. This is what rhinos' horns are comprised of. So this is very tough stuff. So you will develop those, and you will have actually significant protection when you're running around the ground. That all being said, these aren't normal surfaces to run on. Running on concrete, broken glass, things like that aren't really natural surfaces, so our natural defenses might not be able to still accommodate for that. And that's where running shoes really come in. They provide sort of superior protection for your feet and comfort than barefoot. So again, you could do it naturally under natural conditions, but we live in unnatural conditions. But the few things that running shoes actually do negatively impact in our running, and that's how we run mostly, and a lot of it's also the impact and how we develop as a result of that. So for example, the running shoes do provide superior protection for the bottom of your feet, but now your feet aren't touching the ground. You know, they're not experiencing what's happening. So if you were to walk around, even if you develop very thick calluses, you still have access to this information. And our feet have a very involved sensory network, and that provides real-time, immediate information about what the terrain is like, so you can make small-scale adjustments, and it really helps to strengthen your foot and respond, again, to differences in terrain. If you were to run with shoes on, you're going to deny your feet that information, and you're just going to transition surfaces as if they're all the same, and that can cause again, your feet to develop weaker because you're not reinforcing those muscles, not using those sort of stabilizing muscles, and at the same time, you're not really getting information, so you might be more clumsy as a result. Running shoes also have a significant impact on how we run, the form of how we run. So to think of that, let's just walk around first. So if I show you how I'm walking barefoot, you simply just taking your heels striking the ground, then you're transitioning weight to the forefoot, and then you're sort of pushing off. Then your next heel hits the ground, then you add your weight to that foot, and then you push off to your next stride. So that's how you normally do it. If you think of this as a graph where you're looking at the force you're applying to the ground over time, then you could see that when your foot first hits the ground, your heel first strikes the ground, you're going to get a large impact peak because you're delivering a lot of force to the ground right now. You're starting to put your weight on that foot, and it's coming crashing down on your heel. And now you're going to gradually add weight to that leg, loading onto the ground, and then you're going to push off, which is going to have a more force push to the ground. So initially, you're going to see this sort of initial jarring sort of impact, and then it's going to go back up and then increase as you're sort of pushing off. So that's how it normally works when you're sort of walking around. If you were to do that when you were running, your heel would strike. So now you're not just kind of walking from one stride to another. You're really sort of bounding onto the next foot. So if you were to bound onto the next foot and strike your heel first, that impact would be much more substantial. You'd have a significant impact peak when you first really hit the ground. And then you'd carry on, you roll towards the middle of your foot again, and then you eventually push off to launch into your next stride. But you would only do that maybe once or twice if you were running barefoot, hitting your heel on the ground, until you immediately notice that is not the way to do it. So then you would essentially take your heel out of it for the most part, out of this equation. And now you're essentially going to land on your midfoot, and then you're going to accept that energy, sort of flex your muscles, load that energy into the springs of your Achilles. Your arch, which is normally dome-shaped, is now going to start flattening out, and it's going to take a lot of energy you would be delivering into the ground. It's going to store that, and you're going to deliver some of that back out and push off with that to your next stride. So if you looked at that graphically, and you could see how you're delivering force to the ground, it'd actually be more of a very smooth, sort of hump-shaped graph, because ultimately you're not having this jarring impact peak. You're gradually sort of loading onto this leg. You're gradually applying force. At the same time, you're loading these springs that you're going to then launch off with. So that's sort of the proper way. That's the ancestral way to run. And you can imagine that running and landing on your heel, not only would that be incredibly uncomfortable, but it's also not efficient. If you're leaping from one foot to the other and you're landing on your heel, you're basically going to be braking. You're in a stopping motion at this point. And then now you have to sort of recharge and then push off again. So it's not efficient. Your foot's on the ground for longer. And it's also not really beneficial for using the adaptations that you actually have for running. So again, all of this is lined up so that your leg you impact the ground here. So everything's supposed to line up to accept it sort of here. If you land here, things aren't lined up as they should be. So not only are you loading joints with stresses in odd sort of angles that they're not really used to, but at the same time, it's much more pronounced because you're running. So running on your midfoot is actually will save a lot of your these injuries, and that's why sometimes people think of, oh, why is running supposed to be so natural? Then why are injuries so common? And a lot of it is because of improper running form. So that's where running shoes really, again, come into play here. So a couple things to point out about running shoes and why they can be sort of be problematic for running. And that's this built-up heel right here. The built-up heel, it forgives you from that initial jarring heel impact. So if you have the shoe on, and then you land on your heel, that impact is actually absorbed quite a bit. So you're not punished for that. So you don't immediately sort of correct and then run the normal way. You could just kind of keep carrying on, just throwing your feet at the ground. So this heel will actually essentially promote heel striking as running as opposed to midfoot striking as running. And that's just not the way to go. And again, that's why you can really experience some nasty injuries in ankles, knees, hips, back. Those are individuals generally that will use their heel a little too much when they're running. Granted, if you were used to heel striking and now you're transitioning to sort of midfoot striking, which is the more naturalistic way to run, you're going to run into probably newer issues, such as your Achilles. Might get extra sore nowadays, and you can also have plantar fasciitis is a common thing. It's where basically down here in the bottom of your foot doesn't really like it too much, and again, it's because you're loading your foot now. You're asking your muscles in your feet to absorb that impact. You're asking your Achilles to absorb a lot of that forceful impact instead of the heel on the running shoe. But ultimately, if you can build those up, then you will be running much more efficiently because you're using those springs. So another issue with running shoes, and this actually influences the development of your feet, is that the shoes are stiff. Most running shoes you have aren't going to just completely taco when you try to bend them. They should have some stiffness to them. And the reason for that is because it actually does what your arch is supposed to do. So your arch is supposed to form this sort of rigid dome, and then when you hit the ground, it flattens out to spring. So it'll flatten out, and then it can spring off again. And running shoes, a helicopter. So if you use running shoes, you're essentially denying, or you're reprieving your arch of doing most of the work. The running shoe is taking over the responsibility there. So that's why we find nowadays a lot of people have flat feet, and what flat feet are essentially is when your foot hits the ground, your arch immediately collapses. It's not this rigid dome that will straighten out and then spring you back. It just flattens out and doesn't do any sort of springing back. So it's much less efficient. Individuals with flat feet have to spend about 17% more energy when they're running. So running shoes will actually, because they're sort of saving you from having to do that yourself, they ultimately cause those muscles to weaken, and you don't really develop that sort of rigid arch, so you can be susceptible to flat feet if you, again, running shoes. And that's actually something that is very recently in the news. Nike had this sort of Breaking 2 project, this initiative to have a marathon runner break 2 hours in the marathon. And they had these fancy shoes. It's actually a version of these. Basically, what they did in the shoe is they made almost an artificial arch on top of already the rigidness that's in there. They put a carbon fiber plate, so every time an individual would take a stride, it would flatten out and push off. So essentially it's doing the job of their arch, but then some. So you can imagine if you're helping your arch through the springing action every single step, and you're taking thousands and thousands and thousands of those steps, you could see that there would be an advantage. And that's, you know, that's why it worked. So ultimately, those shoes are going to help with performance. But if you trained in shoes like that over time, other muscles are going to be doing the normal work, but the arch will be doing less of the work, so you'd end up running into a problem there. So probably great for competing, but not great for training. So yeah, that's really all I wanted to talk about on running shoes. But definitely walk around barefoot a couple of strides, and walk around with shoes in a couple of strides. Take a couple of strides barefoot running, and take a couple of strides with shoes on running. And if you notice huge differences in your stride, that's something to actually now think about and consider.